The last module divided all of our machine learning algorithms into two groups, supervised and unsupervised. Now we're going to discuss another way to divide the same machine learning algorithms into two other groups, parametric and non-parametric. It is important to understand parametric and non-parametric learning so you will understand what is the best type of algorithm to use given your dataset. Here's the oversimplified version. Parametric is trial and error learning, and non-parametric learning is about counting and probability. So if we think about our little machine learning cloud, it has two settings. As you can see, we really have four different types of algorithms to choose from. An algorithm is either unsupervised or supervised, and it is either parametric or non-parametric. We'll be talking about all four types. Whereas the previous section on supervision is really about the type of pattern being learned, parametricism is about the way the learning is stored, and often, by extension, the method for learning. First, let's look at the formal definition of parametric versus non-parametric learning. For the record, there is still some debate about the exact difference. A parametric model is characterized by having a fixed number of parameters, whereas a non-parametric model's number of parameters grows with the size of the training set, and you can potentially have even an infinite number of parameters. As an example, let's say the problem was to fit a square peg into the correct square hole. Some people, such as babies, just jam it into all the holes until it fits somewhere. This is like parametric learning. Someone older might just count the number of sides, 4, and then search for the hole with an equal number. This is like non-parametric learning. Parametric models tend to use trial and error, where non-parametric models tend to count. Another example of parametric learning is trying to learn the mean and spread of a Gaussian or bell-shaped distribution. We can estimate the parameters from a sample. Now, increasing the sample size does not make the problem any more complex. That is, the number of parameters will be the same irrespective of the size of the sample. Parametric learning is basically trial and error learning using knobs. Supervised parametric learning machines are machines with a fixed number of knobs. That's the parametric part. And learning occurs by turning the knobs. Input data comes in, is processed based on the angle of the knobs, and is transformed into a prediction. Learning is accomplished by turning the knobs to different angles. If we're trying to predict the probability that the Detroit Tigers will win the World Series, then this model would first take data, such as sports stats like win-loss record or average number of toes, and make a prediction, such as 98% chance. Next, the model would observe whether or not the Tigers actually won. After it knew whether they won, our learning algorithm would update the knobs to make a more accurate prediction the next time it sees the same or similar input data. Perhaps it would turn up the win-loss record knob if the team's win-loss record was a good predictor. Inversely, it might turn down the average number of toes knob if that data point wasn't a good predictor. This is how parametric models learn. Note that the entirety of what the model has learned can be captured in the positions of the knobs at any given time. One can also think of this type of learning model as a search algorithm. We are searching for the appropriate knob configuration by trying configurations, adjusting them, and retrying. Note further that the notion of trial and error isn't the formal definition, but it is a very common property to parametric models. When there is an arbitrary, but fixed, number of knobs to turn, then it requires some level of searching to find the optimal configuration. This is in contrast to non-parametric learning, which is often count-based and, more or less, adds new knobs when it finds something new to count. Let's break down supervised parametric learning into its three steps. which aren't too different from the steps of non-parametric learning. Step 1. Predict. To illustrate supervised parametric learning, let's continue with our sports analogy where we're trying to predict whether or not the Tigers will win the World Series. The first step, as mentioned, is to gather sports statistics, send them through our machine, and make a prediction on the probability that the Tigers will win. Step 2. Compare the truth pattern. The second step is to compare the prediction, 98%, with the pattern that we care about, whether the Tigers won. Sadly, they lost, so this is our comparison. This step simply recognizes that if our model had predicted 0%, it would have perfectly predicted the upcoming loss of the team. We want our machine to be accurate, which takes us to step 3. Step 3. Learn the pattern. This step adjusts the knobs by studying both how much the model missed, 98%, and what the input data was, sports stats, at the time of the prediction. It then turns the knobs to make a more accurate prediction given the input data. In theory, the next time it saw the same sports stats, the prediction would be lower than 98%. Note that each knob represents the prediction's sensitivity to different types of input data. That's what we're changing when we learn. Unsupervised parametric learning leverages a very similar approach. Let's walk through the steps at a high level. Remember that unsupervised learning is all about grouping your data. Unsupervised parametric learning uses knobs to group your data. However, in this case, it usually has several knobs for each group, each that maps your input data's affinity to that particular group. Let's look at an example where we assume we want to divide our data into 3 groups. In this dataset, I've identified 3 clusters in the data that we might want our parametric model to find. Group 1 is red, Group 2 is blue, and Group 3 is green. Let's propagate our first data point through a trained, unsupervised model. Notice that it maps most strongly to Group 1. Each group's machine attempts to transform the input data to a number between 0 and 1, telling us the probability that the input data is a member of that group. There is a great deal of variety in how these models train and their resulting properties, but at a high level, they adjust parameters to transform your input data into its subscribing groups. As I mentioned before, nonparametric learning uses counting-based methods. Nonparametric learning is a class of algorithm wherein the number of parameters is based on data instead of predefined. This lends itself to methods that generally count in one way or another, thus increasing the number of parameters based on the number of items being counted within the data. In the supervised setting, for example, a non-parametric model might count the number of times a particular color of streetlight causes cars to go. After counting only a few examples, this model would then be able to predict that middle lights, always, 100%, cause cars to go, and right lights only sometimes, or 50%, cause cars to go. Notice that this model would have 3 parameters or 3 counts, a count for each of the lights, indicating which lights were on or off when cars were going or stopping. If there had been 5 lights, there would have been 5 counts, or 5 parameters. What makes this simple model non-parametric is this trait wherein the number of parameters changes based on the data. In this case, the number of lights. This is in contrast to parametric models, which start with a set number of parameters and, more importantly, can have more or less parameters purely at the discretion of the scientist training the model, irrespective of data. Another example of a non-parametric method is KNearest Neighbor. Let's say we have a bunch of data. When we are given a new input data point, our algorithm has to make a prediction about which group the new data point is in. It takes the average of the k most similar known data points. So, in effect, what constitutes the parameters of the model is the data points themselves. As the number of data points grows, so do the parameters of the model. If we get more and more data, we can say that the parameters of our data are unbounded or infinite. Now, our parametric model from before seemed to have a knob for each input data point. In fact, most parametric models still have to have some sort of input that is based on the number of classes in the data. So you can see that there is a bit of grayness between parametric and non-parametric algorithms. Even parametric algorithms still are somewhat influenced by the number of classes in the data, even if they are not explicitly counting patterns. The term parameters is actually very generic. It refers only to the set of numbers used to model a pattern, without any limitation on how those numbers are used. Counts are parameters, weights are parameters. Normalized variants of counts or weights are parameters. Correlation coefficients can be parameters. It's simply referring to the set of numbers used to model a pattern. As it happens, deep learning is a class of parametric models. We won't be discussing non-parametric models further in this course, but they are a very interesting and powerful class of algorithm. In this unit, we have gone a level deeper into the various flavors of machine learning. We have learned that a machine learning algorithm is either supervised or unsupervised, and either parametric or non-parametric. Furthermore, we have explored exactly what makes these four different groups of algorithms distinct. We have learned that supervised machine learning is a class of algorithm where we learn to predict one dataset given another, and that unsupervised learning generally groups a single dataset into various kinds of clusters. We learned that parametric algorithms have a fixed number of parameters, and that non-parametric algorithms adjust the number of parameters they have based on the dataset. All these concepts will be important as we start writing actual code during the rest of this course. Deep learning leverages neural networks to perform both supervised and unsupervised prediction. Up until now, we have stayed at mostly a conceptual level, gaining our bearings on the field as a whole and our place in it. In the next unit, we will be building our first neural network, and all subsequent chapters will be project-based. So pull out your Jupyter notebook and let's jump right in.